Hi, we're going to continue the discussion on dimensional homogeneity by bringing you a few more examples. Okay, so this problem, they tell us, when you have a shaft and when you twist it, apply torque to it, and it's going to have an angle of twist. This angle of twist, later on, you're going to learn in strength material class, it's going to be equal to TL over JG. That's a formula. And over here, they say the T is going to be the torque. Torque given the unit is Newton meter. And they also give us L, it's the length. So if it's length, it's going to have a unit of meter. Then J, it's called a polar moment of inertia. And we do not know, for this particular problem, we don't know what's the unit. That's what you're solving. And this G is the shear modulus. And that's going to have a unit of Newton per meter square. Okay, so you're solving what's the unit, what's the dimension for J, polar moment of inertia. Okay, so how do we solve this? And first, I will suggest to substitute all the known units into the equation. And this is angle of twist. Angle of twist. And this angle is going to be in units of radians, right? Not in degree. Radians is going to basically means no unit, dimensionless. So that's my left-hand equation. And the right-hand equation, I have torque, that's Newton meter. And L, it's length, that's in unit of meter. And J is something we're solving. Then G is shear modulus, Newton per meter square. So I will continue work on my right-hand equation. So I have Newton, and Newton can cancel out. Then I have meter square on the top, and then I have 1 over meter square at the bottom. So basically it becomes meter to the power 4th, right? Then over J. Again, you're solving for J. And now let's look at left and right hand. They have to have same dimension. Left hand is radians. Radians means dimensionless. No dimension. So the right hand have to be what? The same thing. It's going to be dimensionless, which means there's no dimension. Okay, so if that's the situation, what do you think this J have to be? J have to carry on a unit of meter to the power 4th. Then they cancel out, right, when they do division, and there will be no units left. So we figured out that for this problem, this polar moment of inertia gonna have a unit as meter to the power 4th. Okay. Now let's look at some other example. All right, so in this example, they have this beam. It's cantilever beam, kind of like a diving board, right? And then they have some kind of forces acting on it. And this is omega. And then they give us this in x dimension, and this entire length of the beam is L. Again, this is what you're gonna learn in strength material. They give us the equation, they call this deflection of the beam. So deflection of the beam, which means when you have a beam, used to be this original shape, and now when you apply force it, we can totally visualize it's gonna bend it, right? It's going to bend down, the diving board going to go down, and that's your deflection, how much has been deflected. And every single, at different location, at X location, you're going to have a different bending deflection, right? At the tip end, right here, you're going to have maximum deflection. So they have this equation figured out for us. They said Y is going to be a function of X, and this is negative omega x squared, 24 EI x squared minus 4LX plus 6L squared. So in order to solve this problem, we are going to write down the units that's given. Here they told us they give us this y is deflection. Deflection y here it's gonna have a unit. They said the deflection is in units of meter, right? It's a distance. Then here W is what we are solving. It's distributed load. We don't know the unit. So that's question mark. And this E is elastic modulus. It's going to have a unit of Newton per meter square. And I is moment of inertia. And our second moment of area, you can call that as well. It's going to have a unit of meter to the power fourth. And X is distance from the support. So that's going to have a unit of meter. Then L, it's the length of the beam, gonna also have a unit of meter. So knowing that, we're going to put this in the equation. Y is deflection, and then equal to. Now you have something interesting here. You have a negative value. You also have a 24. They all are constant, right? Does constant have a unit? No. So in that situation, we don't need to worry about it, because our goal is to look at the dimensions. So I'm gonna actually ignore them. That's the strategy you'll be using. Just ignore those constants. So now immediately we're gonna get into omega. Omega is what we are solving. So omega right here. Then we have X. X is the distance from the support. That's in units of meter, so it's meter square. Now we come into this entire thing in a parenthesis. There are three things plus minus together. Remember, if you can add them or subtract them, they have to have the same dimension, right? Because we can add a foot, 6 foot plus 4 foot together, but we cannot add a 6 foot plus 4 Newton together, because they're not the same dimension. Again, if they can plus and minus together, they have the same dimension. And you can verify it. X squared, that's going to have a unit of meter square. And all those two other terms going to have a unit of meter square too, right? Again, you ignore the negative 4. That's a constant, does not have a dimension. Same thing, ignore 6. So when you add all those meter square together, what's the dimension you will have? Meter square. Don't tell me it's 3 meter square, right? Because it's the dimension you're worried about. It's meter square. Okay. So knowing that, so the whole parenthesis is going to give us a unit of meter square. Then look at the bottom. E is elastic modulus, going to have a unit of Newton per meter square. I, moment of inertia, is meter to the power 4. Now again, just write down the left hand meter and the right hand. Well, we are solving for those omega, and then here we have meter to the power fourth, and a Newton meter squared times meter power fourth. Then that cancel out. What do we have over here is going to be the unit for omega, and this is Newton per meter square. Then you can solve this. Again, what we are solving was solving omega here. What's the dimension for the omega? It's going to be Newton per meter square times meter. That's give us a unit of Newton per meter. That's our distributed load dimension. Is every meter along that beam, how much force, how much Newton is applied on. That's distributed load. So here you are using the dimension homogeneity to figure it out. Okay.